experimenters. I'm Seth Noir. The man behind the camera with the exceptional handwriting is Yassine Alout. And today, we're going to be finding the acceleration of gravity by studying a free-falling object. The object being this bob here. And now this bob will be suspended between these two wires, and it will fall between these two wires to the ground. Now, also between these two wires, there's going to be an electric potential difference of voltage that will be controlled by this box here, this multi-frequency spark timer. What this is going to do is it's going to release a spark every 1/60th of a second. That's going to be 60 sparks every second. That's astounding but true. Alright, so now, let's see here. So now, I'm triggering the spark, but nothing's happening yet. That's because the wires are just far enough apart that no sparks will come out. So I can cause the sparks by two ways. I could either move the wires a little closer together, or we could put a piece of metal in between here. Metal like this ring on the bob. Yeah. Alright, so now, to gather information about where the sparks happen, we put a piece of wax paper in between the two wires. Now, what will happen as the sparks are triggered by the object, it will leave burn marks on the paper. And by studying those burn marks, we can get the data we need. So now, this is held aloft by an electromagnet. So let's take a look at this. This is the electromagnet. Let's see where it goes. There are the wires there. And then, aha, here is the box that controls the electromagnet. All right. And we also have the detonator. The detonator is what releases the electromagnet. It's not actually a detonator. I'm just living out my childhood fantasy through all of you. The detonator is what releases the electromagnet. So, let's turn it on. Position the bob suspended from the electromagnet. Excellent. One hand on the detonator, and the other hand will activate the sparks. Ah, excellent. Excellent. Turn everything off. Now let's see what we have. Ah, look at those burn marks on the paper. And also notice that the marks are getting farther and farther apart, as they ought to. As they ought to. All right, terrific. So now we take this, and we go to our table with a 2-meter long stick. All right, so now we want to tape this on the table. So I tape one end. Be careful not to put tape on any of the marks. The other way. And we want to make sure it's nice and smooth. No ripples. Okay. And then we want to put the ruler on the 6th mark. On the 6th mark. Now, come on over here. Now, there's a couple motivations to why we want to start the 6th mark and not the first one. The first one is we want some sort of initial velocity on our starting position. And also, to minimize fractional error, we want to avoid the smaller measurements. In other words, the smaller the measurements are, the more fractional error has an impact. So let's see here. 1, 2, 3, 4, 5, 6. That's our starting point at time 0. So at time 1/60, that's 1. 260, that's 0.2, 3, and so on. And then we want to put the 10 centimeter mark. Now, the reason why we want the 10 centimeter mark is at the end of these, they're usually all mashed and nasty, so we want to start the 10 centimeter mark. Put that at the 6 dot, and it'll look like this. It'll look like this. We'll tape the ruler down also, and when we tape it down, we want to tape it down where it's secure, not a lot of wiggle room. And when we tape it down, we also want to make sure that we can see all the dots and they're lined up with the ruler. And also I want to observe on this example here that sometimes the sparks miss some dots. In other words, in this example, we have 6, 7, 8's missing, 9 missing, then we just continue on from 10, 11, and 12 is missing too, 13, 14, all the way up to 20. All right, so for this particular example, we have 3 less values in our data. What can you do? All right, so now we start at position 0, and that's, I read the next one, position 1. Let's see, I read that as 12.49, but remember, that's really 2.49 because we're adjusting for the 10. And the next one, let me take a good look, 15.51, good, good, good. Next one, 18.72, and let me see, 25.96. Okay, great, and then you go on through all your data points, and let's see what we do with this. A table. We put in the table the time values versus the y values. Once again, be careful to adjust for that because you started at 10 centimeters. And then we graph y versus t. And now we got to be careful here. Some of you might look at this and say, I know what to do. I'm going to put a line. No, no, no. We know better. This isn't linear. This is a parabola. Look, this is the relationship that we expect. Y is 1/2 gt squared plus v naught t plus some sort of y naught. And so the y naught that we started with is 0. So that's 0 giving us this. The 1/2 gt squared plus v naught t. Now, you could use Excel to get a 2-dimensional polynomial equation. And you will actually get 3 numbers here. In other words, you get a coefficient for the t squared, a coefficient for the t, and then a constant at the end. Now, all I'll say about that is I suggest you think about all those numbers and compare them to what you get at the end. Interesting to ponder. Say no more. All right, but we do want to linearize this. So, going back to this, we could linearize this by dividing everything by t. All right, in other words, we'll get y over t will equal 1/2 gt plus v naught. So this will be our y equals mx plus b. So we'll need another column. We'll need another column for y over t values. So take the y and divide it by each t to get another column, and then we're almost there. We graph it, and it should be linear this time, the y over t versus t. And then guess what? The slope should equal 1/2 g, meaning g is 2 times the slope, and you're done. You found the acceleration due to gravity. Congratulations. I'm going to go back to play with the detonator.